machines upgrade perfectly.
Oh yeah, they upgrade perfectly, but nothing will run.
I haven't had anything failing to run. It's interesting. Sorry to hear.
Well, I hit the record button, so let's get our meeting started. Welcome to the Propeller 2 live forum on Tuesday, December 22nd. And it's a day earlier than normal. Everybody adjusted. Thanks for that. And I guess the communication around it wasn't all that confusing. Otherwise, you would not all be here. So today we're talking about analog inputs. And I asked Chip to respond to a really simple customer inquiry where a person just wanted to see how to do some simple analog measurements, and I do too, because we are now in the beginning of the process of starting to collect up things that we see and capturing them for our website in the form of little projects or quick bites. We aren't really sure what we're going to call them yet, but basically things that people can browse and go to and run. Load and run, because examples are what we learn from and examples are what are missing. So my plan over the break here is to start to get a few pages of those together from some of the things I've seen here. I mean, it might be as simple as blinking an LED, measuring analog input for starters, and then we'll just grow it from there. So Chip has some code, which I will retrieve from my email after he starts talking, and then paste a link so we can all get to it. And later that code will appear on our website too, so don't worry if you don't get it along the way. So where we are, today we have some new people. I want to welcome them. We have everybody from teachers, hobbyists, scientists to enthusiasts here. And some of us are just blinking LEDs or haven't blinked an LED, and others are doing audio projects. So we're all over in terms of skill level and capability. And what I want to tell you about that is that it takes us a long time to get the pieces in order to make the P2 really easy to use for people. A little look at our history kind of can show you how things happen, but Chip's been making microcontroller tools or chips really since 1997. And we end up with the silicon in our hands before we even get to finish all the tools. So we get the chips and then we put all the pressure on Jeff to make the software, and then we start creating examples. But some people inevitably come to us and say, where's the book? I want the What's a Microcontroller book for the P2. Where is it? Well, that takes years to get. Like, just look here, 2006, the Propeller 1 came out. I think it wasn't until 2013 we had the activity bot. And it wasn't until 2017 when we had Blockly. So give us some time, but we'll get everybody started here in due course. So everyone's invited to join this, and there's a whole lifetime of learning ahead of us with this, which is super cool. Next, actually tomorrow, if you'd like, you can sign up for this. So Johnny Mack is going to take us through a project where we use some WS2811 RGB LEDs, an LCD, a rotary encoder, real-time clock, and a temperature sensor to make a holiday light contraption of some kind. And actually I have part of it here working on my desk, so I will show you that before I turn over to Chip. So this is just my P2 Edge and my Johnny Mac board running some of the LED light code John produced, and then some of the other parts that we'll be using in tomorrow's meeting. And tomorrow's meeting is the first of a series of 4. And there are some parts that we suggest you have, but if you don't, it's okay. We have them available in a bag that keeps coming and going from Parallax because they come in stock and then you buy them and then they run out of stock. However, on our website, there's a link to all these pieces and they're all from Amazon. So you can get them if you'd like individually, but there's some cool things like a little I2C LCD, and these are really low cost. It's kind of scary how cheap they are. So the links are on the events page of our website. But you can really join in without the hardware because John will probably give us a lot of basic introductory stuff tomorrow anyway. And this is what the parts look like. I'll share you a link to that. So they're on our site as the P2 Liveform Holiday Kit. And if you go there, you can scroll down and then browse to the various resources that go with it. Through this, John's going to give us a whole lot of new cool objects to play with. And also, by this time next week, we'll have Stephen Morocco's Hub 75 LED hardware in stock. And the 2495 will have 20 boards to put out there, and I'm trying to get the panels too. He just pasted a link to the panel in the chat. And there's excellent resources that have been developed around that are still being developed.
I got a bunch of those panels off of eBay.
Ah, okay. What format did you get? Resolution and number of pixels?
I have to check. I was using them on, I had some 8085s for some old stuff that I was using, but let me look it up and I'll send you a link to it.
The key thing with these, Ed, is that they are Hub 75. They have a special driver with them. So
all right, I'll look.
Okay.
If it's not Hub 75, I won't bother with it. I'll let you know though.
Thanks. So Chip, you want to talk A to D now? Chip, do you copy?
Yeah, I just can't. Something happened, but I'm back
Okay.
now. Did you want me to start talking?
Yep. And while you start, I will go retrieve your zip
Hold on.
file.
I just added one file. I realized there was something we should talk
Okay,
about.
you can add that, then send it to me again.
All right. Can you talk for another 30
Yeah,
seconds?
sure. Okay, so Chip has a zip file of several A to D input programs, from simple to like I think 8 or 20 of them in parallel to awesome. And the thing is with these programs that I figured out when just trying to run them is, since we're in the early adopter phase still, you have to run them with Peanut. Okay, and maybe someone can paste a link to the Peanut download in the chat window, all right, because they use the debug command, and that debug command is not like serial formatted for Parallax serial terminal, but it has the graphical controls in it. So to run these as written, you need to use Peanut. But Jeff, who is here, is working to, hi Jeff, is working to add these additional capabilities into the prop tool, which is our more formal release. So for those that have been hanging around here, this is not new news to you, nor is it confusing, but to newcomers, this kind of thing is sometimes a stop. But there are approximately 60 of us here who can help you out. So we ask for your forgiveness as the tools are still evolving.
All right, I'm ready.
Okay, I'll go find your zip. Thanks, Chip.
All right. Okay, thanks. So what I'm going to talk about today is how to use the ADC. I was going to do the DAX also, but I worked all night on this stuff and I didn't get any further, but we can do the DAX another time. They're just as simple as the ADCs. But anyway, I have some stuff to show you about how the ADC works. So what I'm going to do is I'm going to try to share my screen here. Let's see. Let me get into a folder first. Wait a minute. Oh, here it is.
And while Chip preps up, if you want to ask questions as he goes, you're welcome to do that. Just unmute yourself or type it, whatever. We don't have any formal rules here, except it's somewhat G-rated.
All right. So I'm getting it
until it's not.
Switched around. Uh-oh, not found. Oh, I need power.
And also, Lachlan, since you're here, will we get to see a MicroPython example of an analog input today?
Yes, we've been using LM334 temperature sensors, which are a really common current source version of the temperature sensor. It's really neat in that it's only got the 2 wires to connect to the P2. The P2 does the biasing, and the nice feature about the LM334 is that you can tune it to sit around the midpoint of the A2D, and that lets you zoom in on a signal, so you get quite a good sensitivity when you apply a temperature change. So yeah, happy to run through that when you're ready.
That's great. It's like Christmas time.
Must be.
All right. I'll get going here. Is that okay?
Yep.
Sure.
All right. So let me share my screen. Portion of screen. Okay, you should be seeing here my little Pnut program. Can everybody see this?
Yes.
Okay. Can you also see my camera still? Is that available in any view?
Yep.
Okay, so I'm going to take my camera over to here. So I have here a P2 Edge and this Johnny Mac board, and I have here a little potentiometer, and I have the ends of the potentiometer connected to ground and 3.3 volts, and the center tap, the wiper, is going over to P0 right here. Okay, so the idea is that when we turn this potentiometer, that voltage on the center tap that goes to P0 is varying between 0 and 3.3 volts. So what I have here, can you also see the screen where we have some debug display going on?
Yep.
Okay, now if I turn this knob, we can see I'm going to turn it all the way up. We get about to 13,727 or so. If I turn it all the way down, we go to about 3,000. And what's happening here is with this code right here, let me set this back. I set up here 100 megahertz. It could really be anything. It doesn't matter. I've got my pin set to 0. Now to put the pin into ADC mode, it only really takes this. The pin start is a command in Spin2 that does a short sequence of things. It resets the pin. I'm not sure on that. Actually, I should look at the description, but it then does a right pin, a right X pin, and a right Y pin, and then it turns the DIR high. So it's the process of configuring a smart pin. So in this case, we're saying we want this pin here, and then this is taken, these two values are taken from the Spin2 documentation. The P80C1X configures the low-level setup in the pin for analog input at 1x of the actual pin. So it's a full-scale input. And then P80C selects the ADC mode. And 13 selects how many clocks. That's an exponent. So 2 to the 13th is 8192. And this is a sync 2 filter that's going on. So this produces a 14-bit result. That's why we saw things going towards 16K on the high end. And then Y was not used. So we just set it to 0. So what this does, this starts up an ADC pin. At that point, the pin begins doing conversions. It's doing 14-bit conversions. And at any time, we can do a read pin like this. And here's our pin that we're looking at. And I write this to the variable I, and then I just output it to the debug. And I wait 100 milliseconds so we don't go too fast. So when I rerun this program and pull the debug back up, here we can see things happening. Now you notice that when it goes all the way to one end to the other, it's not going from 0 to 16K. The reason is that this PWM thing never reaches 0 or 100% duty cycle. Its max is, it's like it goes between 16 and 83% about. And it's necessary that there be some kind of oscillation in there so that we can resolve things rapidly without having to wait too long for pulses. So this is to read, you know, to register this to 0 volts and 3.3 volts requires another step. It's like a line equation, where what you'd want to do, the ADC has internal calibration settings. You can connect the ADC instead of to the pin at 1x, you can connect it to ground and VIO, which is 3.3 volts. And you could take measurements at both of those points, and you could solve for a line equation. So you come up with a scaling factor and an offset. It's like the old y equals mx plus b problem. And I'll show in a little bit a program. In fact, I can show next what that looks like. But wait, first I'm going to do a few other simpler things that build on what we have here. So you can see that to get a smart pin going in ADC mode, it's really there's nothing to it. This is all explained in the silicon documentation, and then pin start is briefly covered right now in the spin 2 documentation. But once you set up a pin in this mode, which is going to be sync 2, this puts it in sync 2 mode, 13-bit. All you have to do after that is just go and pick up the samples whenever you want them. Now you could set this up in assembly language so it alerts you every time a conversion is done, so that you have everything, you know, that can be your time meter. Or you could pull it and you get an event. You'll know that a new sample has been resolved, so you can go pick that up and use it. So this is doing 1 pin. Now, are there any questions so far about this?
Chip, you said that the clock frequency doesn't really matter.
No.
Not at all?
No, well, you know,
At some point it does, but
I can set it as low as 10 megahertz. I mean, that's what we need to do debug. And we can see the values that are coming out. Here's one end. And then if I go to the other end, it's close. Like, let's look at that top end value, 13,740. Now I'm going to switch things over to like 300 megahertz, right? We're going to go 30 times faster. Now we're at 13,720. It went down by 20 counts, or maybe about 0.1%. So, but that can be taken out with a calibration procedure. So this thing can work over a wide frequency range. In fact, while we're on this, let me just show a picture. This is actually something that someone made. It's on the forum, and they posted it. Let me slide this thing into view here. You guys see this little picture? You see a schematic?
We do.
Yeah.
Okay. So this is a simplified drawing of what the ADC is. It's actually pretty simplistic. It's more complicated in the implementation because we have some very high impedance current sinks and sources with an active load it can switch between to keep the noise on the capacitor here very, very low. But what happens is these are just digital. You see these two inverters in series. That's literally all they are. They're just logic inverters in series. And we actually have 6 of them in the ADC. But we show 2 of them here just to get the point across. 6 of these things in a row, of course, are going to make a very fine decision based on what's coming into the first inverter. It gets amplified up, and by the time you get to the D input of the flip-flop, resolved to a 0 or a 1. On the clock, that gets latched, and then immediately the inverse of that is fed back through this high impedance current source and sink back to the integrator cap. So this is the process we use. It's called a delta sigma A2D converter. And it's very simple in principle, and it's pretty effective. It has very high linearity. And in our case, because we have very high impedance current sinks and sources, it really doesn't matter what the input threshold is of these inverters, because it's not just the input threshold of the first inverter, it's the set of all 6 together, because as it feeds through all the inverters, the first inverter has the most effect on the threshold, but the second is contributory all the way out to the sixth. But that voltage in the first inverter is going to be not always the same. It's going to vary from A to D to A to D. It's going to vary based on what the supply voltage is. But because we use high impedance current feedback, that doesn't matter. That gets kind of pulled out of the equation. So this doesn't need to be exactly VDD over 2. It doesn't need to be 1.65 volts. It might be 1.6 or 1.8, or it's all dependent upon these tiny little inverters that have to make a very quick decision. So this is the whole feedback loop. And this thing can run at hundreds of megahertz. There's not a lot going on. So that's what's at the core of the A to D right there.
And
We
Chip,
do have,
what's
yeah.
the max sample rate with 14-bit resolution?
Okay, so 14-bit resolution takes 8,000 clocks, 8192 clocks to resolve, right? So we could say, let's say we're running at 300 megahertz. Let's see, 1, 2, 3 divided by 8192. It would run at 36 kilohertz for a 14-bit sample, right? But if you wanted, we could multiply this by 2 for 13-bit samples. You go 73 kilohertz. If you want a 12-bit sample, that could be 146 kilohertz. If we multiply that by 16, 2.343 megahertz for 8-bit conversions.
Chip, how do you specify the number of bits? Is that the 13 in your program?
Yeah, it's not. Yeah, Ken thought it was a carriage return, but it's 13, meaning do 2 to the 13th clocks for the conversion. And because we're using a SINC2 filter, we wind up with 1 more bit resolution than that. So over 8192 clocks, we resolve 14 bits. And that is about the practical limit of the A to D hardware in the pad. If everything is set up nicely, you can get between 13 and 14 bits of resolution. But it doesn't make any sense to go any higher than that. At that point, you're dealing with noise inside the ADC, and you really can't resolve better. I'd like to, at some point, if things go forward well, I'll redesign the ADC and improve it in a few ways. I'll improve the noise floor, and I'll improve the conversion rate by adding maybe 15 parallel integrators so that we can get 4 bits per clock instead of 1. Anyway, okay, I'll pull this out. So that's how the ADC.
So is that helpful as a simple example for one channel A to D for everybody?
It's very simple, but I'd like to understand how accurate, how stable is the conversion? That is, in terms of DC, for example, if I put in volt 0.65, will I get a volt 0.65 over?
Yes.
Yes, you're right. Will it stay or will it wander?
Sorry. Yeah, well, let's do that. I'll jump to another. Okay, I'll just zoom. We're going to come back to some stuff I was going to hit later, but I have a thing here called ADC to millivolt. All right, so let me expand the window here a little bit. Now, what this program does is it launches another cog. Let's see, how big is this thing? Well, I'll just let it be this big. So we have up here. Here's our program. Instead of doing what do we call a pin start, we're doing a cog in it to actually launch an app in another cog. And then we use a debug to show what it's doing. And this is going to do a conversion on a set of 8 pins that are all in a row. So what this program does here is it configures 8 contiguous I/O pins to be ADC inputs. And then through this process right here, it's kind of a stateful process that it goes through. Every process, or every state, it does a, let's see, I think I used, where's my right pin? Let's see, right here. You see this 9?
Mm-hmm.
So that's going to do a 10-bit conversion, okay, in 512 clocks. And it's going to do 8 of them per pin. And it does this over time. And so every state, it converts all 8 pins, but what it does is it adds them together and then interleaves in this fashion. You see this table down here of like what happens when.
Mm-hmm.
See the cycles. The first cycle, it takes all the conversions and adds them to their different level bins.
And
then
what's the purpose of this?
It's
Why
to
are
solve,
if I have an A2D, and if I want to have a single accurate DC representation and digital representation of a DC voltage, and I want it to be stable from sample to sample, do I have to average a lot of them in order to get that result? That is, will it stay like a voltmeter?
well, I'll show you. We'll run this and we'll see what it does, and you'll see.
Yeah, but why do we need 8? I mean, why are we talking about 8?
Just because we can do 8. That's the only reason. There is no.
So what you're saying is here we have 8 voltmeters.
Yes.
Giving us 8 outputs, and it's going to, and actually you're answering my question. So I have to assume that the proof of the stability will be that all 8 will stay the same.
Right. They all run independently. So
was that the reason that you're doing this for me?
Yeah, this is like an instrumentation type ADC.
Yeah. Okay. That's okay.
Yeah. So you see, just all by itself, the A to D converter can resolve dynamic signals very nicely. There's no need to calibrate anything if you don't care about absolute DC level. However, if you want to do some kind of instrumentation work, you need to do calibration. So see, there we have all these states that we go through, these cycles, and then in each cycle we have, well, let's see, how do I break this thing down? We have 4 states that we go through, 0 through 3. So what we do is we have to be looking at the ground and the 3.3 volt reference and doing conversions for those as well. So what we do is we interleave, we do a ground calibration, a signal calibration. We do a ground calibration, a signal measurement, a power calibration, then another signal measurement. So every other measurement is for signal, and every one in between is for either calibrating power or ground.
Yeah, I see. And that would mean, for example, for your, since you can do 14 bits in about 30,000 times a second, that would mean that actually the topmost for accurate instrumentation grade conversions would be 10,000 times a second.
Yeah, it could be something like that.
Okay.
It's a little bit squishy, and it's very dependent on how well you keep your power supplies quiet. The power supply to the set of 4 pins that the A to D is working on, because we have unique power pins for every set of 4 IOs. So what we have on our P2 edge module and our P2 evals, we have very low noise, low dropout regulators to generate those local 3.3 volt supplies.
Fantastic. Yeah. One thing, if I may interrupt for one more question from this, I'm in France and it's very late. So I noticed in P1, the P1 A2Ds, you have the circuit shows 2 capacitors, one to positive and one to negative to the inputs, right? Yeah. Why, how does that work? I mean, I don't have much care.
Okay, huh? So an integrator really only needs, I'll pull my little drawing back in here. An integrator only needs one cap in theory, right?
Right.
But in practice, it's good to break that cap into 2 parts. Bias one part to ground and bias the other part to the positive power supply. So what you get is like common noise rejection.
So that it's a matter of balancing out the noise.
Yes. Yeah. So in our implementation in the chip, we actually have, caps to ground and caps to 3.3 volts.
Is this cap inside the P2?
Yeah,
Or is it-
everything. Yeah, this is all
Oh.
inside the chip now. This
So,
is
so
why.
that is an improvement then from the P1.
Roughly, yeah, but it's a much better circuit. It's a lot lower noise. See, the
Uh-huh.
trouble with the P1 is there's a lot of turnaround time involved in getting a pin to go all the way into the counter, then latching it, you know, and then re-outputting the opposite back over the I/O pin. Well, this is literally what goes on in the chip. So
I see.
there are no longer these long propagation delays. Instead of propagation delays totaling maybe 12 nanoseconds, this propagation delay is like 1.5 or 2 nanoseconds.
Fantastic. I get it.
Okay.
That's a major improvement.
Yeah, and there's a lot of stuff I could do to improve this some more. I'd like to have the chance in the future. Because I think we could just keep making it better and better. And it's a very small circuit. Every pin has one. And also what we have, there's actually an analog front end where you see this pin pad coming in. There's a resistor there. And we can actually, in the P2, you can select which resistor you want to go through. So we actually have we have 1x mode, and it's done logarithmically over 6 steps. We have 1x, 3.1x,
Fantastic.
10x, 31x, and 100x.
Fantastic. Yeah.
And so when you get to the 100x mode, you have a full voltage span of like 33 millivolts, or maybe 40 millivolts, because before you hit 0 to 100% duty cycle. So if you can AC couple, just bring in an AC signal in through a small capacitor. You could feed it to the ADC. The ADC will auto DC bias it where it needs it to be to do this process. And you can resolve all kinds of AC signals. So you could demodulate carriers and do all kinds of stuff.
Yeah, great.
So I'll show you this program we have here. So this looks like a lot of monkey motion. I mean, there's a lot of steps here, but in order to be able to solve this line equation with repetitive recalibrations that are needed, you have to make a program to do this, right? It wouldn't really suffice to go measure ground. And other stuff goes on too. When you switch the resistor around inside the ADC, you have to go through a little dead time to allow the circuit to settle, right? It's nice if you have the same signal coming in all the time, but once you switch away and you go to something else, there's all sorts of new DC stacies that have to level out, to get below an LSB before you can start converting again. So that's what this little program does. It's an assembly language program, and from beginning to end, here's some data for it. But the code is the main loop of the code is just what you see on the screen here, right here. That's the main loop of the code. And this runs on an interrupt. And then up here at the top, this is the whole setup for it, where it says ADC program setup.
I didn't know you had interrupts in Parallax.
We do in the P2. Yeah, now we used to have in the P2 hot, which was an intermediate thing we were working on, but it was going to take 8 watts if we implemented it. It was not practical. So we had like there's a word for it, is it preemptive multitasking, where every 2 clocks, we would switch from one set of program counters and flags to the other. And so you could actually have 4 concurrent programs running, which was really cool. But because you could have a cog running 4 separate programs, taking care of things all in high bandwidth. But that just took too much hardware, too many flops. It was going to run too hot. So I had to redo things, and I added interrupts because now we can't run programs on such a tight timing basis. But with the smart pins, which can go out and tell you when something has completed, you can use that to trigger an interrupt and then deal with it. So this program here, in fact, look, here's the main loop of the program. Whoop, right here. It doesn't do anything, okay? Because this ADC ISR right below here, this is what runs on the interrupt. this is the main loop. You could actually put a whole bunch of code there to do something.
Mhm.
You know, because it's really doing this ADC process in the background.
It becomes transparent after you simply have an ADC
Yes.
logically and mentally and theoretically, or not
Yeah.
theoretically in practice. You can forget all of that once you have once you know what your parameters are going to be. Yeah. Excuse me.
And this could run. This could even run within the Spin2 interpreter. I have a version of this that runs. This thing runs in the Spin2 interpreter, interrupting your code as it executes. But you never know that. It just takes little pieces of time here and there.
Yeah.
The trouble is, though, when I wanted to do this debug business, it was taking so much time from the interpreter and blocking interrupts that this thing here would kind of like lose sync.
Yeah.
It stole enough time that it
must have been one of your pleasurable moments.
Well, I had to redo the way it works. So I took the program and put it into another cog. But I mean, you could make it do a lot more right here, right? I mean, you're not using the streamer or anything. You could do a whole another application right there. But I had to separate it from the Spin2 cog that was doing the debug stuff because the debug was stealing too many cycles. So what this thing, it's saying here, whenever we configure any kind of pin for anything, you can actually do, you can do up to 32 pins at once. So this add pins operator here.
Chip, you got to run this code pretty soon. Control F10.
Right, I'll run the code. So what it's going to do, it's going to take from pin 0 to pin 7, and it's going to run all these parallel conversions on it, right? And so let's see, I'm going to hit, and I'll drag this up here so that we can see it. So I have, so that's 8, and these are millivolts, right? It's resolving down to millivolts.
You mean it's 3.293 millivolt? No.
It's 3,293 millivolts. And so
that's almost 3. That's almost positive supply then.
Yeah, it's connected to the positive supply. Now, as I turn that potentiometer down all the way to 0, there.
Great. How about turning it halfway?
Okay.
Exactly
and
halfway, Chip.
And not breathing, and don't breathe on the potentiometer.
Okay, here, I know what you're looking
Let me
for.
see, I want to see this.
Okay, there, I'm not touching it.
1.644, 1.64742. Yeah, that's pretty.
Oh, no, only look at the first one. The others are floating.
What?
Okay, only the first one. The first column is the potentiometer. The other are high impedance and they're floating.
And but how come they're in the same range?
Oh, because it auto biases to nearly VDD over 2.
So actually, your technology means that the CMOS inside your chip is very similar. I mean, they all match. They all have the same analog curves.
Yeah, they're close.
They're close. Yeah, that's fantastic.
Okay, so watch this. I'll unplug. Okay, I just unplugged from the P0, right? And now I'm going to plug into P7. So now I'm going to now I'm controlling the last one. So everything is floating, but the last one is now connected to the potentiometer. So I'll turn the potentiometer all the way up.
I see, yeah.
3.299. And if I turn it all the way down, it's reading like.
Yeah, fantastic. Yeah.
Very low. And you know.
But the other ones should go down too because they're floating, no?
Well, no, they're going to auto bias to whatever the midpoint
is. I see. Okay.
And that midpoint is what's determined by that innermost inverter I was showing you. You know that chain of 6 inverters?
Yep.
Chip, am I understanding this right? The first column that you read was 3 point something. Was that in millivolts?
Yes. Yeah.
All right, so the last column you have there now, that's outputting microvolts.
Oh, no, it's, no, I'm sorry.
Yeah, it's not
See, the
3 point.
No, it's
underscore-
volt.
It's not 3 point something millivolts. It's 3 point something volts.
Yeah,
Okay.
so millivolts, see, we're using an underscore like in lieu of a comma
Comma.
in America, right?
Okay.
So if I turn it all the way up, it's the 3,299 millivolts. So it's all the way up at the top. Now I can take like, let me get a little jumper here, and I will jump. I'll take ground. I'm going to connect ground. I'm just going to hardwire it to P0. So this is the first column. There. Now I've got the first input is now connected to ground.
3.2.
Yeah, see the first column,
yeah.
how it's like 0, 1, 3, 4.
Right.
These, and now this is the P2 edge. If I do this on the P2 eval, it might be a little bit quieter because the PCB layout was more careful. But in the future, I want to redo the way inside the ADC on the pad. I want to redo the resistor arrangement, and I'll get a lot better calibration. So we can go like, we can probably calibrate to like 0.1 millivolts. Whereas right now you see we're jumping around a few millivolts.
Yeah.
Especially towards ground. It's a funny thing, it doesn't happen on the top end, it happens on the bottom end. I'm not really sure why that is.
Hey, Chip, regarding the auto biasing, can you run your fingers over those middle pins?
Yeah, oh, good idea. Okay, so let me do this. So let me free up some stuff here, unplug some things. I'm gonna unplug everything.
And how many pins like that you have that could float? 32 or 64?
You could do every single pin this way. So now they're all floating, right? So I'm gonna put my finger, I'm gonna touch ground, and then I'm gonna touch the 4 pins. Okay, I'm touching ground now. And if I let off, it goes up a little bit. So let me lick my finger. There we go. Now I took my finger back off.
How about static?
Well, the pin is designed to withstand 2 kV human body model. So it would, if it got zapped, you'd see a reading probably jump up or down just briefly.
Yep.
If I had a bunch of jumpers, I could actually, short all these to ground. Well, okay, well, I'll do this. I'll take 3.3 volts. I'm going to connect 0 to 3.3 volts. So the first one is now, let's see, why isn't that doing anything? Oh, yeah, the first one is now tied to the power supply. You see it's reading 3,293 millivolts. Now I'll connect like pin 4, right? That's the 5th one in, is now connected to the power supply.
Right. Clear.
Yeah, so if I can get, if we have the chance in the future to redesign the ADC, I'm gonna clean this up quite a bit. So we're gonna get these things trimmed a lot better. And we'll have higher conversion rates. Now I'm gonna unplug everything. So now they're all floating again.
But dynamically, for example, when your A2D audio or music, this would not be such a problem.
No.
That the noise could be filtered out because it's actually very high frequency, right?
Yeah, and you don't care about DC when you're listening, when you're recording
No,
audio. So
absolutely, yeah.
So you can completely skip all this calibration stuff. So
Yeah.
the calibration slows things way down, and it's now there's a big problem that we can't get away from. Although better design could probably fix it a little bit. There's this phenomenon called 1/f, as in frequency, 1/f noise. So you really want to be able to take your conversions in the smallest time possible to eliminate 1/f noise. But when you have to do multiple like calibration readings and signal readings, the
You get
time
1/f.
stretches out, and you get more of this noise that it's like a rumbly. It's like low frequency rumbly noise.
It's sharp noise.
Maybe it is. It's like just random noise, but it's low frequency in nature. It's not high frequency. I mean, it goes down to 0 millihertz. You know, it's very low noise, but
it increases 6 dBs per octave.
yes, yes. Yeah, so this is another thing, but this is how the ADC is working right now. Now I'll show you, I'm going to close this thing. Let's
Okay,
see.
and does anybody else have a question they're afraid to ask? Now's a good time while Chip switches gears.
Lachlan had one in the chat window there. He was asking Chip, the P1 pin diodes were rated for 500 microamps. Are the P2 diodes similar?
Oh, you mean like the substrate diodes? I'd say probably like 30 milliamps or something.
Oh, wow. Okay.
I mean, you could do a lot more than that even, but I think if you exceeded like 200 milliamps, you could have a latch up problem. But that's, you know, that's only going to happen if you're connecting things to pins that you probably shouldn't, like, you know, motors and weird loads and things that, you know, would require like some kind of transistor interface too. All right, let me see here. I'm going to grab another file here. Oh,
Ken, this is one of those lectures that we're going to have to look at many, many times. You're recording it and you're going to post it, aren't you?
Yeah, absolutely. And I have questions I'm afraid to ask that I don't want to ask Chip to repeat 20 minutes of what he said, but I'm still wondering why the other 7 channels were showing a similar value to the pot. But
no, they weren't similar. They were just the floating stasis values. And see, with nothing connected,
nothing on them.
Yeah, with nothing on them, those pins are going to float near the middle. And so they're like 470 k ohms. It's very high impedance. So it doesn't take a whole lot to influence them. But left to themselves, they're just going to float somewhere in the middle. But the signal that you're driving into them is going to overcome that high impedance.
Just not used to what to do with the abundance of A to Ds. I mean, my prior experience is like an ADC 0831 with 1 or 2 channels.
Yeah. It's very exciting to have so many. I think it's a challenge, and it'll be very interesting for someone to do something with it. For example, I just bought something like 20 piezo electret microphones with leads. Well, I could imagine those connecting all 20 to the P2 and getting something off. I don't know what it's going to be, but it might be interesting.
Are you interested in audio inputs then?
I'm interested in both DC and audio. Audio is my field, but DC is I'm into analog synthesizers, music synthesizers.
Well,
and I know
have some
Chip
friends here.
Interested. I know Chip is interested in music.
Yeah.
So,
yeah.
I was the one years ago, I think, that asked Chip to talk about Fourier transforms and how the P1 did it. And I suspect that the P2 will be able to do it very elegantly. And of course, I'm not unfortunately, I'm not a coder. I'm a very good analog designer. And that may be the membrane through which I may not be able to pierce into using the P2, but it's exciting, you know. So
I have some. The P2 with the Cordic is really nice for the FFT because you can do one coordinate rotation and it takes care of like 4 discrete normal steps to compute because really what all this sine and cosine transformation does in the FFT, it's a coordinate rotation. It all is about rotating an X and a Y around 0, 0. So we can do that with one instruction with the Cordic, and it turns out really nicely. It simplifies the heck out of the FFT. So all you wind up looking at is a couple of discrete adds, and then all of the funny pointer movement, you know, increment and test and loop. And I don't know what that file's called, but it's in here somewhere.
Chip, while you get your next demo ready, I'm wondering if we should have intermission and see some MicroPython.
Yeah, sure.
If everybody
That's
can
good.
tolerate the break for a moment.
Okay, let me do a stop share here.
Okay. Lachlan, you okay with that?
Yep.
Great. We'll go to Australia then, where it's the middle of summer.
It is, although it doesn't feel like it today. But look, we've been experimenting with MicroPython and the LM334 current sensors, which translate temperature into an analog current signal. One nice thing about using the P2 is that you can use the inbuilt bias resistor, 15K bias resistor, to get results. I should just say also that these screen captures and code and everything I've posted into the P2 forum this morning, so that, or this afternoon your time, so that you can see, code and screenshots if you want to try this out for yourselves. I'm just gonna, maybe I can do a screen share here. That might be the way to go.
And it's my hope, Lachlan, to take that example and to put it on the Propeller 2 section of the website.
Sure. Okay, so let me just bring up. Easy to do this. Okay, so this is the LM334 temperature sensor as we're using it, hooked up to the P2 evaluation board. The red wire here is connected to 3.3 volts on the corner of the header. And the white wire here is the analog signal, the current output, which goes into pin P19 on the P2 evaluation board. This potentiometer here is a 10-turn potentiometer, which allows you to set the operating point. And what we are able to do is actually make this operate around that sensitive 1.65 volt region of the A2D, that Chip was describing, how the pins sort of float around that region. Every A2D pin on the P2 has a built-in zoom capability. And so you can zoom in on signals around that range, and that'll be useful for things like microphones, the piezo sensors as well, probably, that Sergi was just talking about. So this is a good example of actually being able to zoom in on a signal and get sort of extra sensitivity out of the P2 pins. So that's our configuration. Here's the data sheet for the LM134 or 234 or 334. They're all the same device, but just with different temperature ranges. They're not super accurate, but the big advantage is that you can buy them from pretty much any electronic shop. I think DigiKey and Mouser sell them for about 80 cents each. And of course, with the P2, you can put one of these on every single pin if you want to, or if you need to. All right, so crossing into Mu. This is just a static screenshot of our code in Mu. Down in the bottom left corner, we've got the MicroPython interactive window, like a terminal. And in the bottom right, we've got a plot of the temperature that the temperature sensor is seeing, which will show running live. I just want to show in the code how easy it is to set up a smart pin for something like this. We're basically in MicroPython telling it that we have a pin 19 that we're interested in, and we can use the shorthand of P, just a short single variable P for referring to that pin from then on. What we then do is configure the right pin to have a 15K ohm pull down resistor. We want to turn on the analog to digital converter with a 10 times zoom range, which means it looks at that 1.65 volts plus or minus 165 millivolts, so in that kind of range. We want to count how many high pulses there are out of Chip's ADC converter circuit, and this TT bit at the end just enables the analog to digital conversion at the same time as biasing the pin with a 15K resistor. We then tell it that we want to take 1 million samples at a time. This is kind of an accumulation bucket, and it just means that the A2D converter will go out and take 1 million 0 or 1 readings before returning a result. And so if you had the thing exactly at 1.65 volts at midpoint, you should get a return of 500,000. We turn the pin off, which seems counterintuitive, but that's just to enable this 15K bias resistor. So we're outputting a low, and that brings that 15K low bias resistor into play. And then we go into a plotting routine here where we take a number of results every 150 milliseconds and plot them in the graph. So what I'll do now, I'll cut across to the live mu screen, and we will click run here and let it start accumulating samples, which it's doing now. And you'll see how the graph in the bottom right-hand corner is updating. If I put my fingers on the temperature sensor, I can increase the temperature, and it'll sort of zoom in a bit closer in a moment. So that's increasing the temperature. I'll just hit run again. This time I've got the can of freeze spray here, which I'll take the temperature down negative. I'm applying that now, and you can see there's a big temperature dip, and then I'll put my fingers back on again and I'll warm it up fairly quickly. So this is a combination, fairly simple demonstration of mu and what it's quite good at doing, just plotting results into a graph in the bottom corner there. So this is pretty much it. This is just a simple demonstration of how to read a current sensor. The nice thing about the LM334 is that you can set that bias level so that you really do get close in. And what we can do, we can go into the 100 times zoom range and zoom in, and you'll see that, so instead of these values here being sort of plus or minus a few 100,000, you should get even more now. Actually, let me just check. It might be a bit ambitious. Maybe go 30 times. The A2Ds also have a 1, a 3, a 30, and 100 times zoom. Right, so this is a 30 times zoom. Putting my finger on the sensor now, and you can see that's quickly heating up. You'll note there's not a lot of noise there. I mean, there is when you sort of zoomed in a super close way. Okay, we're actually clipping, we're going sort of, you know, we're actually hitting the limits of where the sensor reads. So look, practically probably 10 times zoom is the right way to go with that sensor. I've posted this code and screenshots and examples and everything into the P2 forums. So this thread here, connecting P2, has got the screenshots. And then just finally, I was going to shout out to Tracy Allen from EME Systems, who did this neat document on how to construct a little LM334 probe using heat shrink, and, you know, just a practical guide to how to build this thing. Instead of using a 226 ohm resistor, we're using about 635 to work with the P2. But, you know, there are reasons, depending on where you want to sort of measure most accurately, you can change that resistor. It's pretty straightforward.
Lachlan, a quick question for you. Line 9 of your Python code, so now I see how it works because you explained it, but prior to you showing it today, how would I have figured out how to do the A to D?
Right, so Chip's Spin 2 documentation has a list of commands you can send to the pins, or a list of predefined constants which you can configure the pins with as shorthand for setting up the A2Ds.
It's the same thing you showed in Spin then?
Yes, yeah. We use the same constants as used in Spin, and I think also in FlexProp GUI, you know, I think the same constants are available, so at least we've got the same tags, I guess, for setting up pins and configuring the different modes and configurations.
Yeah, they are the same in FlexProp also.
Nice. Any other questions for Lachlan?
Yeah, I was wondering if you could show us where you do that beautiful strip chart graph in your code.
So that's just down in this section here. first of all, we just take a baseline reading, which gives us effectively a 0, and that just means everything's always centered on 0, no matter where it sits in the range. We always effectively start from 0. So it just displays that baseline value, and then after that it goes into this loop here. And all that loop is doing is taking a p.read pin, which retrieves the latest result, subtracts off that baseline to make it sort of reference to 0. And that is outputting, if you look at the terminal down here, you'll just see that it's just putting brackets around a value in mu, and that basically sets like a tuple that mu is programmed to interpret this. And if you have a comma and more than one value, it will display more than one trace. That's something we can probably do another week, you know, with a multi-channel version. I don't think this will.
So is Lori in a good mood?
Here, this is running 4 or 5 channels, and although, because I haven't got things hooked up, these are sort of all coincident. You can sort of see there's 5 channels in there. So you're basically just sending a vector of readings in to mu, and that
To be clear, it's a feature of mu that does the graphical display from the text output. It's not any Python code.
Right. When we get some time, we'll also do this with a debug display, so that you could do the same thing from spin. You know, at the moment we can only do that with Propeller tool, but sorry, with Pnut. But when that sort of goes into Propeller tool, we could do the same thing there, and effectively get like a debug display happening inside of the Propeller tool environment.
Very nice job.
Yeah, thank you. Ken put us onto mu. He's been using it for a lot of educational workshops. And, you know, initially we thought it's maybe it's sort of fairly focused on just getting results and things, but sometimes that's what you need to get going, you know, and then after that you can always translate and build on this, and you can actually build pretty complicated programs. I know Brian or OzPropDev, who's here in the conference today, has built things with around 1,000 lines of code in mu successfully. So, yeah.
Thanks, Lachlan.
No problem.
That's another example. We'll harvest for the website. I just ordered 10 LM334s while you were talking, so I could set them up on 10 channels and get out a torch and do graphing of waves.
Yeah.
Chip, still with us?
Yep. Thanks for that, Lachlan. Can you guys see this screen here?
Yes.
Okay, so you remember the first one, the first simple example, it just had 0, right? So now we're doing 16 pins. So we can start up 16 ADCs all at once, because this value of pins has these upper bits added by add pins that say how many other pins to add in. So this line is actually the same exact line in the first simple example. But now we have to go down here and we have to read all those samples separately in a loop, right? So I have this samples buffer right here, and we load it up right here. Once it's loaded, we can then output that as an array to the debug screen. So when I run this, we can see now we're getting 16 conversions. And Sergey, you were thinking about stability. Well, look, here's the thing. When we don't have to go through those extra calibration steps, we get much better signaling. You can see that well, my conversion count is lower. I'm only doing a 10-bit conversion. So let me go back all the way up to like a 14-bit conversion. I'll rerun this thing. Let's see. Zoom is making my things kind of funny here, but okay, now on the first column there, that's pin 0. That's where I have my potentiometer connected. So if I take it all the way down to ground, you can see we're only getting a couple LSBs of movement. right? It's pretty, and this is out of a 14-bit conversion. If I crank it all the way up high, we're getting a few steps of noise in this conversion. So if you don't have to do, if you can get by without the calibration, you can get better quality conversions.
Yeah, I see.
Okay, so we could expand this to 32 as well. But what I did here for that demo, because that gets to be too wide, we can't see it all at once, right? So I have, let's see, here we go. So now this example will do 32 pins, right? But I'm going to use a debug terminal so that we can see it all, because I have to reformat the way the data is displayed. So now we use a debug terminal. It's going to improve things, but we still go and fetch the samples, but now we display them using this debug terminal. So when I run this, let's see, where did, let's see, Windows, there's a funny thing that goes on between the Zoom software and my app. I mean, oh, here we go. All right, it appeared up here. So now I can bring this into here. So now this is better formatted, right? So it's easier to see. So we're at 0, 0. That's pin 0, right? So that's all the way up. I'll turn the pot all the way down. There it is at the bottom. Now I'm going to move that center tap all the way to P31. So it's now going to be the last one.
Okay.
Yeah, see the very bottom one?
Yep.
It's up at 13,000. And I can turn it all the way down to 3,042. So here it's converting 32 pins and then displaying. So you could do the other port. You could do all 64 pins, but it would take 2 steps, right? Because you can only address a block of 30 pins, have to be addressed in sets of 32, of which there are 2 sets on this chip. So this is all pin 0 through 31 or 0, 0 through 1F, running conversions, just open loop, and you can go and at any time you can grab the samples like this, just read them in, and then put them into an array, or you could make an assembly program to always deposit them into an array, so that's always available. Okay, so that's the same thing. Now there's one other thing I've prepared here. Let's see, is this it? Yeah, okay. So the pins have a couple of modes. You can just straight read the ADC bit stream. You can read it in blocks of 32 bits at a time and get the exact data that came out of the ADC. You could run a totalizer like what Lachlan was doing, where he'd look for a million clocks and come up with how many were ones. But the Sync2 filtration is better because it's gapless. It takes care of the endpoints, which become noisy. Noisy because it's like you're breaking you're splintering a stick, and now you've got shards. With overlapped Sync2 or Sync3 filtration, you get rid of those endpoint issues, so you get very smooth samples. So we have Sync2 and Sync3 filtering. Sync3 filtering resolves like more bits than Sync2. I think it adds like a couple more, or how does it even double? I think I have it in the docs. It's not clear in my head right now. But aside from Sync2 and Sync3 filtering and being able to totalize or capture the actual bit stream, we have what are called scope modes. So that in the pin, and let me pull up I had a document ready to go here. Let's see, hold on. Hopefully I can slide this into the window.
Does debug have a scope mode in which you can just see waveforms at the place of numbers?
Oh yeah, we're going to use it right here. Okay,
Get ready.
Here's my problem. Okay, so I'm going to go down to the smart pin. Oops. Okay, so check this out. I'm going to try to move this into the window where the Zoom share is happening.
This will keep you awake past midnight in France.
Yes, it's already 12:15. But I'm ready.
Can you see these filters?
Ah.
So Within
Oh,
the smart pin, there are
very
different,
good.
there are flip-flops. And what we can do is we can treat them as a big, like a chain, right? So we shift the bits into this big chain of flip-flops. We have maximum a 68 tap 2-key filter, and guys on the forum help work all this out. But what's really neat, the way this filter works is, imagine you have all these bits, these single bits from the ADC. They're sliding through this filter, right?
Mm-hmm.
And they're weighted. So that what you do is you multiply the 0 or 1 for the bit times whatever the level is for that tap, and you sum them all together on every single clock. But that's too much silicon to compute. But we found that we could double integrate and use the incoming bits and outgoing bits and certain bits at certain tap points. And we could control these integrator values to actually realize these filter functions with nothing more than like an 8-bit adder or compound adders. Actually, I think it was more than, it's like maybe a 13-bit adder, but we take the top 8 bits. So we can, in scope mode, we can realize these filter functions so that every single clock you get an 8-bit sample out. But it's not, it's 8 bits in magnitude, but it's really not 8 bits in quality, because with 68 taps, you've only got just a little over 6 bits of real DC resolution, right? Because the log 2 of 68 is going to be 6 point something.
Mm-hmm.
So, but it looks better than that when you see the waveform. So here's.
I see.
Oh, wait. I moved the wrong thing. Let me get this out of the way. Okay, back to this program now. So we can see this, right?
Not yet.
So what
Okay.
we're doing here is we're going to set up, I set up the scope for debug, 4 channels. And now I set the pins up for scope mode. You see that PADC scope?
And you, why is the filtration needed for scope mode?
Well, because
I'm sorry to be so simple, but
because you can't, you have, what we're going to do is we want to see, we just have a limited resources in the smart pin, right? We can dedicate 68 flops to a big chain. And so we want to use that as like a storage. So we shift every ADC sample into that thing. So
I see. I'm beginning to see. You mean you're filtering so that your array will look nice.
Yes.
I see. So it's not a sort of see.
Yeah, I mean, we could do something like we could just add up every time a bit goes in, a 1 bit goes in, increment your DC. Your reading. Every time a 1 comes out of the other end, decrement it. The trouble with that is it's noisy, right? But by having these nice side lobes in these filter functions, it smooths out and becomes way better.
Right.
Okay, so, getting myself into trouble here. Let me get rid of this. Okay, so back to this code here. So in this case, we set up scope mode, and then we set up triggers. So every scope pin also has two 6-bit trigger values, but they're moved up 2 bits. So we're going to say when you go from 78 to say 88, that's a trigger, right? And we can then look at the pin to know when it went. It first has to arm at 78, and then when it goes over 88, because of which one's higher versus lower, it sets up the slope direction. So in this case, this is the first. We arm at 78, we trigger at 88.
Okay.
And then this controls what filter function. 0 is the 68 tap 2-key. That's the nicest looking one, but it's the lowest bandwidth one. So then we have an assembly language program, some inline assembly here, that waits for a trigger on the first pin. And then it does a capture using the streamer. It just, right here, we control the frequency, and we set the streamer mode up, and we say capture 512 samples. And then we wait for that job to finish. And then we send that data to the scope. So when I run this program, okay, now let me get some action here. I gotta go. take, oh, you know what? I'll use the other. I have the other board because it's a little quieter. I'm going to use the P2 eval because it just worked out better on this one because it's a lower noise board. Now,
No.
so I have my function generator here is making a ramp, right? I can select a square wave, sine wave, and I've got 4 channels here. And like if I connect, I can take that channel 0 and also connect it to channel 3, I guess it would be. Let's see here. I'm feeding in on one.
Yep, can I ask a question?
Of course.
Would all this kind of output be compatible to using a program such as processing?
What is processing?
It's a program for taking the data from whatever you're doing and putting it in a graphical format. I used it on one of my Parallax projects where I had a bunch of pings, and instead of trying to see stuff in lines of numbers that the pings were putting out, I had them put it in. I went into processing and had it come out as a graphical interpretation. So each ping was represented by a circle, and it got bigger or smaller on a graphical background, so I could actually see what the pings were doing without having to think about the numbers and see the numbers.
Yes,
and I could look at these circles get bigger and smaller.
Well, if ping can accept serial
it's very popular.
input,
it's used a lot with the Arduino and other processors. That's why I was wondering.
Okay, so I mean, if we can send that thing serial messaging or load a file to it, that would work. But we have facilities in our debug.
Yes, you can.
Okay, then you could do that. But within our debug setup, we have like I think 11 or 12 different debug displays. Like this is a up to 8 channel scope display here. And we also have a plotter that you can use for any kind of purpose. And you could send it live data. You just have to, write the command codes for it so that it drives it in the way you want. But you could do all that stuff using the built-in debug facilities in Pnut, which will soon be in Propeller tool also.
Yeah, to John, who just sent a question. If you go to my YouTube channel, which you can probably just find by Carol Hazlett YouTube and Google it, I do have some demos there using different Parallax sensors.
Okay.
And the processing is picking up the data coming out. You can set it up in many different ways. The thing with processing is you can, it's a very easy graphical interface to use, and it's Java oriented, so that you can take whatever's coming from your serial output and give it backgrounds and graphs and whatever you need to make it all very good. The reason I'm asking is because more people know processing than would know this, and it'd be easier to use, and definitely for me since I know processing. But this is all kind of like, what the heck is he doing and how's he doing it?
Carol, this comes from processing.org.
Yeah, processing.org. That's it.
Okay, thank you.
I think it's a matter of time before somebody makes some examples that use processing to graph. Just checking it out, it looks like it's a matter of substituting PS or serial object and then formatting it the right way.
I'm going to try it.
That'd be a great project, Carol.
Yeah, because I have used processing with the Propeller 2. You'll see that on, or not the Propeller 2, the Propeller 1. And you'll see that on the few things I do have right now on my YouTube channel of it.
We have, I mean, I don't know how processing works, but I tried to make all of our debug things as simple as possible. So see, here's the scope that I'm using right now. And these are all the commands for it. You have some instantiation commands and then some feeding commands. And that's all there is to it. here we're just sending it data.
I haven't used the debug yet, so I don't know. But it all
Yeah.
looked like the same kind of thing I was dealing with processing.
It's probably similar, but we have quite a few. I mean, we have a logic analyzer, which is, whoops, this thing here. We have an 8-channel scope. We have a vector display with log and normal mode. We have an FFT. We've got.
But yeah, all those tools are readily available or makeable in
Yeah,
processing.
it's
too.
all in the Spin2 documentation. See, here's the general purpose plotter. You could use this to generate all kinds of like live circle drawings to show like how much signal you're getting back from a ping. Here's the little, whoops. Here's a little terminal that I was using before. Here's a little data fed bitmap. You could do whatever you want. It has quite a few different ways you can feed data into it. And then we have different color modes so that you could simulate things that you're actually going to have the hardware do. And we even have like a MIDI thing.
Ah, that's for me. Except I don't use MIDI, so.
Yeah. Okay, let me get this thing out of the way. So,
Chip, before we leave Carol's question, it would be good for us to have processing examples on our website because it's a whole other ecosystem.
yes.
And if anybody wants to produce processing equivalents from Chip's debug examples, which are shown in the documentation he's showing, which are linked from the link that I posted into the chat, we'd love to have them. And I'd be glad to help you with whatever your currency is, whether it's free hardware or robot parts or whatever. Thanks. That includes you, Carol. I know you have time on your hands.
Not so much. You should see what Bill got me for Christmas.
It seems like it should just be a matter of stub converting the serial output from the debug statements to processing.
It looks that way in my little brain.
Or just write processing statements as serial outputs.
Yeah, but it'd be nice if it just worked with your built-in debug.
Yeah.
And parsed it and then just produce processing output.
Does anyone know how many different types of displays there are for processing?
It's a graphical interface, so
it's
really, really functional. There's a bunch of YouTube videos on it. There's a guy named Daniel Schiffman at a university in New York, and he's like the processing guru. He's one of the guys that wrote it. It's really, really a great program.
Yeah,
it's
been around for years.
Yeah, it's probably not fair, but I like to think of it, because I'm an old guy, as the Borland graphics interface for the new generation of things. Like if you remember BGI on that Turbo Pascal world.
Yeah, I've never heard of it. I made a bunch of displays that seemed useful to me, and they're tightly integrated into the whole development tool so that they don't have much overhead. But you know, they're all a little bit unique. I'm sure they're different than processing, but I made them as terse as I could so that you don't have to do a lot of stuff to set up things.
And this will really shine when Jeff gets it into the prop tool.
Yeah, when is that?
Yeah, thanks, Roy.
I was literally waiting to ask Jeff.
Because then we won't have to use any other tools.
I'm hoping to present it next week.
Ooh, nice.
All right.
Go, Jeff.
And then is Gerald here? Because he was working on the C++ port of it. Guess he's not. Chip, did you send him the latest Delphi stuff so he could update his C++?
No, I need to connect with him. I didn't get any like certain ask from him, but I can send it to him. But maybe he'll probably be on tomorrow because I know he knows Wednesdays.
Well, the thing with processing that's nice is it's not software dependent. You can use it with any other language because you're strictly just taking the data coming out of your serial port and that, and then putting it in processing and using the processing based on Java and just writing your whole own output program for that serial data. It just feeds into it. So you can do it with any chip or any program that you want. You know, it's not specific to just one type of chip family or that.
Right.
I started using it with the Arduino, and then I got torn out of the Arduino world.
Yeah, it'll produce
I like your guys'
standalone
chips better.
applications that will run on any platform.
I believe it's JavaScript, not Java.
And it's also got, now they've just come out with a Python add for it, so you're right, Python
Yeah.
too.
It's definitely Java, but there is a JavaScript port of it called P5 Java or something like that. It's in the chat.
Yeah, it's just called P5JS, and it's literally processing API showing up as JavaScript code.
I liked it because it was very intuitive. I didn't have to do a lot of research or anything to find the command or format or whatever I needed to make my data look the way I wanted it to look.
Well, that's what I've tried to do with this debug stuff. If you look at the highlighted code, see here we set up a scope. We're going to call it S. We say where on the screen we want it. How big is it? How many samples? What's the update rate? And then we're using packed data. And then I declare these 4 input channels, give them names. And so I'm saying that the bottom bar is 0, the top bar is 255, and I want that to be 255 tall on the screen with an offset of 10 in the window. And then I only want legends for the first channel. And then here I feed it. And so once that's set up, I can feed it packed data, which is just a bunch of hex, and then it picks the data apart and then fills up the scope display. So when I run it, we get this. Now, if you notice, this up here was 333 megahertz. So what that means is that, and you also see here we have the set Q 8000. That's like full blast. 4000 would be half rate, but this is full blast. So what we're getting is every sample on the screen was a 3 nanosecond. That was at each 3 nanosecond time division what the ADC filter was outputting. And then
what's the frequency of the sine wave that I see?
That's 1 megahertz. Here, I'll make it 2 megahertz.
That's amazing. That's fantastic.
There's 2 megahertz.
It's so nice and smooth.
Yeah. Now see the filter? The filter, a sine wave, you don't really see it on a sine wave, but when I go to a square wave, see the edges are a little rounded because as the data goes through that 68 tapped filter, it takes some transition time, right?
It's slewing.
Yeah, it's slewing, but watch this. By changing this, by going to the next filter setting, a little sharper now. And then if I go to the last filter setting, which is the shortest filter, so we get more.
And you've got some ringing. It's amazing.
Yeah, it's like a little scope. Yeah, and let me see. I'll go to 3 megahertz. At some point, we start suffering attenuation because of the analog front end in the ADC. Here's 4 megahertz.
That's fantastic. That's wonderful.
5 megahertz. See, we start to lose.
Yeah.
You know, but if I go back to 1 megahertz, it's like very clear. And then here's a sign. So see, with these lower res filters, you get better phase performance, but you get a noisier signal.
Yeah.
And then, okay, now you see this is, this here is full blast. Like I can change the sample rate to half. I can change at 80 bazillion to 4 bazillion. And that will, so now it's sampling like every other one. But see, the nice thing about the scope output is, it is a finished filtered result available on any clock. You don't have to wait for any kind of like, time division. You can sample it at any random time. I mean, I could even put in here like 7 or 6, right? And we can get all these intermediate sample rates. I can go down to like, I could put like a 1 there. So now now we're looking at every 8th sample. And this is a sine wave, and then here's a square wave. So
Nice.
with the scope mode and then the streamer being able to capture, it's just like a little oscilloscope, and it captures 4 8-bit channels at once, because that's 32 bits. That's as much pipe as we have back to the main memory. 32 bits. So 32 bits per clock, it's grabbing those scope channels and writing them to hub memory. Last thing I prepared was this scope. Now if I go to like 100 kilohertz, and then if I go to sine, boom, and then I can go back and let's make the prettier filter, because now we're lower frequency. There, that looks better.
Yeah, isn't it? It beats turning knobs on an oscilloscope.
Yeah, you can just do it programmatically now. I mean, we could even go to like, how about instead of, this was 100%, right? But what is this? This is like 1 in 127 or 1 in 128. So if I slow down, let's go to 10 kilohertz. Whoops, that's 10 hertz. Hold on. Yeah, so there's 10 kilohertz being sampled very seldomly. So you can set the sample rate at
Nice.
32
Very nice.
bits of timing precision.
Mm-hmm.
And then this number can be up to 64K right here for how many samples to grab.
And as I understand it, this is one cog doing the sampling, and then one cog doing the filtering?
No, well, the filtering happens in the smart pin. This is all one cog. There's only one cog running here. But
Only
see,
one
what
cog.
it does some little inline assembly to like set up the scope, wait for a trigger, and then capture so many signals. If we didn't wait for a trigger, the data would be all over the place, right? But by waiting for a trigger before capture, then we're getting nice registered data that's repetitive. So it waits for the trigger, captures 512 samples, and then it comes out of there, and then here it outputs those 512 samples to the scope display.
And in essence, your trigger is going to be whenever the input goes from 78 to 88.
Yes, as seen right here.
Right.
Yeah, and that's really the 2 LSBs of each of those values is ignored. But in the case of the lower one, the 2 LSBs are actually the filter number. Yeah, so see, we can
of which
change
there's 30, of which you could make as many as 32, you said.
Yeah, the filter can become smaller. Here's a filter where we'll capture something earlier. See how the beginning it's like
it's setting the threshold.
Yeah. So there's an arm point and a trigger point.
Mm-hmm.
Anyway, that was all the stuff I prepared for today. I didn't have any, I was working all night. I didn't get into the D to A, but it worked out just fine. This has taken like an hour and a half. And we can cover the D to A, which is also, we have parallels for digital to analog to all this stuff I've shown you for analog to digital. We have like, scope mode where you can you can stream 4 8-bit samples from memory at full blast and shoot them to 4 different pins. And we have oversampling smart pin modes that can do 16-bit oversampling. And so there's a lot of stuff like that I can cover next time.
When is the next time? When is before Christmas or after Christmas?
Ken, are you still there?
Yeah, the next time is next Wednesday. Same time. So a little bit late for you. Sorry about that. We could actually have it earlier in the day, too,
That's
since
fine.
many people are on break and they'll be able to attend. So maybe we'll do that. But I think it was good, Chip, that you broke up the A to D and the D to A into two different sharing episodes.
Yeah. Now it's doing a sweep. Yeah, so it just turns out we ran out of time anyway, but.
Well, this is enough for one day. And reading the comments, I think people got what they needed from it. So let's see if anybody has questions too that have not been answered here. So everybody knows now how to do a simple analog input with the P2?
Yeah, if you publish that file, it is easy, but you know, the smart pins, it's such that I can't just off the top of my head type smart pin code. I have to go back to the documentation because there's a lot of little stuff that you can do. And so you need to I have to go back and myself and realize, okay, I need this setting and this setting, and I need to do this way. And so I have to, it never winds up being much code, but there's a lot of stuff possible. So you need to look at the docs to keep it straight.
Yeah, and sometimes the low-level pin settings factor in as well, like Schmidt trigger mode versus regular and stuff like that.
Right. Oh, yeah, there's all kinds of stuff. I mean, you could build just out of the smart pins, you could build, you know, Schmidt relaxation oscillators and then run a smart pin counter on that. And so that you can do you know, LRC to frequency. There's all kinds of stuff that you can do. You could build op amps.
So Chip, a couple questions. What's the amplitude of the waveform? VBB?
3.3, 0 to 3.3 volts. Oh, but you know what? Watch this. Let's go to 10x mode, right? See that? So now we're going to see some horrendous clipping, but if I go to, let's see, my span, whoops, hold on here. Let's see, sine.
More A to D questions while Chip plays with the hardware. We can queue them up here. You could use the chat if you want.
I'm going to make the, now this should be, okay, now look, okay, now I'm getting smaller here. Yeah, now I've got 147 millivolt signal. And I've got it.
Yeah.
The offset is 1.65 volts. So you see now we're at 10x.
You see it?
And I can go further. I could go to 100x. 100x gets really, it's touchy because the center point. So let me just keep dropping this here and see if we can get, oh, almost there.
So while Chip does this for the next P2 live forum, when we talk about the DAC or prop tool, we could move it to Tuesday next week since people are generally on breaks, if that's preferred, because on Wednesday we have Johnny Mac, and I fear that might be a bit too much to have 6 hours of P2 fun in one day. So maybe we should, what do you think? Keep the P2 forum on Tuesday next week?
I'd vote for Tuesday next week.
Okay, and that way for...
Yeah, I'm okay
Tuesday's
too.
good.
Yeah. I'm very interested in the DAC presentation, so.
Okay, and we could even move it a little earlier on Tuesday to help out the Europeans.
No, that's fine for me. If I'm the only European, I work all night, so.
Well, there's another Frenchman who is hanging around, but he had to go to bed, and he's very interested in the MicroPython material.
Good. Well,
we could pull it in an hour. I think nobody else will mind.
No,
yeah, I'm off all next week, so I'm good.
Ça va très bien. C'est formidable. Merci beaucoup.
You're welcome.
Hey, look at this. Do you see this here? Let's see here. Offset. Let me go. Let me lift it up a little bit. This is a 40 millivolt peak-to-peak signal. It's a let's see, what have we got here? what is the frequency? It's 100 kilohertz sine wave, 40 millivolts peak to peak. And then here's the square wave. So you see at the 100x setting, it's very sensitive. So, but this whole thing is just 40 millivolts peak to peak.
Very nice.
And that's its highest amplification.
So if you were to build an op amp from 2 pins or 3 pins, you would that'd be difficult then, because if that's the maximum gain.
Well, yeah, you have a small window, but see, right now I am DC coupling, and I'm telling the function generator that, let's see, it's let's see here, where is it? Its offset is 1.652 volts, right? If I move it up here, I'll move it up 1 millivolt. There, 1 millivolt.
Oh yeah, nice.
You can see it moving here. I'll move it 10 millivolts. Oh, that was too far down. Oh, too far up. But if I were to AC couple this, like if I had a capacitor that was easy to get a hold of right now and I were to put that in line, I could get rid of that warbliness. See that warbly looking thing? How it's kind of wobbling? If I could AC couple, I could get rid of that.
And why is it happening?
I think it's just the ground difference between my test equipment and my board and the power supplies and the PC. I mean, that wobbling is really like 5 millivolts or so, right? Or 3 or 4 millivolts. But if I could AC couple, I could get rid of that. I just don't see a capacitor. Yeah, I just need a capacitor. I don't have one that's easy to get to. Let me look here. Here's a cap. Let's see what's.
Well, the traces that you show are much better than my digital scope, I must say. In my digital scope has all kinds, it has 8-bit, I think it has 8-bit A2Ds. And of course, you see the little steps and the little like pixel things, and they're never stable. Whereas your sine wave is beautifully rounded. So congratulations. I think it's a nice scope.
Oh, thanks. Sorry, I didn't mean to cut you off. I'm just now I'm AC coupling. I guess we still have some wobble in there.
Yeah.
But it is 40 millivolts peak to peak. I mean, if you look at how quiet the flats are, that's like less than a millivolt.
Yeah.
About a challenge, Chip, and do a Lisa Jew with it.
Lisa Jew.
What is that? Is that some kind of pattern?
That's 2 sine waves. You put 2 signals that you put in the X and the Y direction so that they combine and make circles. Yeah.
Oh yeah. I could do that because we have an XY scope mode. We could totally do that. I just don't have. I only have a 1 output function generator though. But you know what? We could use other pins to generate those signals and then read them back. We could use DAC pins and programs driving them.
That would be very exciting for Tuesday to see a function generation with the P2. For example, triangle waves, sine waves, sawtooth, etc.
Yeah,
I just got a function generator for Christmas, so I think I know what I'm going to do.
But you'll have a P2. You don't need function generator anymore.
Yeah, I know. My husband got me a new oscilloscope, a function generator, and a new bench power supply.
This scope, the debug scope, is absolutely beautiful. It really is an achievement. And congratulations, Chuck.
Thanks.
Chip.
Yeah, it was fun. And I don't know if you were here, but I made all sorts of anti-aliased line drawings. Everything that's displayed is anti-aliased. But in this case, because it's like the samples are back to back. There's no distance over which the anti-aliasing could occur. But if I were to like do something like shorten, let's see, if I go here and I put, let's say 200 samples, right? And I capture 200, and here I put 200, but over that longer distance. Oh, well, now we're not registered anymore to our,
Yeah.
oh, I have to change this rate here. There we go. So now there's a little more opportunity for the anti-aliasing. Let's see, where's our frequency sign? I go back to a megahertz there. Anyway.
It's exciting.
So I don't want to derail the fun, Chip, because there's a lot of it happening, but Bart has a non-analog input question to ask.
Okay.
Bart,
sorry to change the subject a little bit. I've been absent from the calls for a couple months now. Day job got in the way. But I've been playing still with digital video, the HDMI modes. And I've explored RDFast and the streamer, and also done some really delved into the Alt-I instructions as well. That's all been a lot of fun. But a couple questions. The first one is, I'm trying to set up, I apologize, I don't have good code to show you kind of the quagmire I've gotten myself into, but I'm trying to set up a like a display list kernel where for any given scan line, there'd be a display list for ranges of pixels. And it seems to sometimes work, and depending on where the, for example, 320 pixels and then 320 pixels of a different color, or 320 pixels from this address to, in the first half of the scan line, to 320 pixels to the second, from a second address on the second half of the scan line. And it's that handoff between the two, like when I have to load RD fast for the second one, sometimes that works and sometimes it doesn't.
Okay. I see. So yeah, so you need to, the streamer will internally buffer 2 whole commands, right?
Yeah, yeah.
So you need to be sure to keep that pipe filled. But are you trying to do more than that? Like, are you trying to have one cog give it a command and then another cog give it a command?
Well, I'm working up to that. And
that would be a little trickier. You'd have to like really be time aligned, which you could probably do at the very outset of the whole, once that little app starts, lock them up, and then thereafter, as long as you agree on what cycle you're on, you should be able to switch between.
Well, so yeah, that was the question I had was about the queuing, because it seems like it's really difficult to kind of introspect what's happening here, but it seems like the streamer commands are queued up, but the RD fast is happening. Is not queued up. Does the RD fast does the RD fast have a queuing as well?
Yeah, it takes I don't know, what is it, 8 to 13 clocks or something, or 8 to 15 clocks. I'm not sure.
Okay.
Look, let's see here. Let me go to the instruction thing. RD fast. 206. Hold on. There we go. Okay, now let me go. It's okay. So it's going to take 10 to 17 clocks.
Okay.
And so that's, I don't know, I see what you're doing. You know what? The only way this is going to work probably is if you could tolerate that much time in your scan line. So you're probably running at 250 megahertz to get HDMI.
Yep.
Okay, so your pixel rate is 10 clocks. So this is the problem, is that you're running over budget by at least 7 clocks sometimes.
Yeah, that sounds right.
And then you have to add in a few more clocks for the X continue or X zero instruction, right?
Yeah, yeah.
Yeah, so so you'd have to really stage your data or have another cog be ready to pick up the second the streamer command left off on the first cog or cog A, then cog B steps in with a queued up read fast to start sending more data. I think that's the only way you're going to do it, unless you can stage all the data, say in the LUT, which, you know what, that might work. You could maybe pre-stage the data. Well, you're going to pull it out of hub memory, so it has to be in the hub.
Yeah.
Or it could be, I mean, you have enough time, you could do discrete commands for feeding it data out of the LUT too. But if you use one cog, you're gonna have to stage your data so that you don't suffer this read fast penalty. Or you're gonna have to have another cog be ready on the spot to do a switch off in one clock, right? And then he takes over.
Yeah.
And you can do that. It's not, I mean, the code for it would be nothing. It's just getting there, you know?
Yeah,
Making sure you're locked up.
Okay. Well, the thing you mentioned about the LUT, I mean, that actually does sound like it would work. But just to bounce an idea off you, I wouldn't be able to do an entire scan LUT. I'd still have to trade off like at least halfway through.
Yeah.
At 24 bits. Yeah.
Oh yeah, yeah. Oh, I see. Because you don't have the memory. If you had, I wish I had put. I was thinking the other day. I wish I had put in a 24-bit. You know, we have like RF byte, RF word, RF log.
Oh yeah.
We have RF vars. I should have made an RF RGB that would grab the next 3 bytes, and then we could have had the streamer use that, and we would have saved a fourth of the memory on big screens.
Mm.
But we don't have that. But anyway, here's how it would work between 2 cogs. Remember that if any cog says an IO pin is high, then that pin is high, right?
Mm-hmm.
So what you want to do is you want to have cog A begin outputting 0 bits. In other words, turn off, basically shut the streamer off so it outputs 0 bits at the same time the other streamer steps on and then starts outputting the next word or the next packet of what is it called? The HDMI data.
Yeah. I think I'll have to work up to that. I think but the timing of where I am right now, it's like it's a little tricky. I'm trying to actually also on top of all of that, do this in interrupt so that it sets up the streamer and the RD fast in an interrupt, and then can go back to doing other stuff in the same cog.
Yeah. You know, we have a guy named Roger. He's in Australia, and Brian and Lachlan know him. I don't know if he's on this thing right now, but he might have written what you're doing right now. Do either of you guys know? Or go ahead, Bart.
Well, from the last time I asked HDMI related questions, somebody mentioned Roger, and they had a driver that could do DVI. But actually the question I had at the time was about audio over HDMI, and somebody mentioned that he actually had a version working, and that there's like headphones.spin2. So that was the second question I had, is if anybody knew where that piece of code was. But yeah, I'll see if I can reach out to him.
Some stuff demonstrated, which Brian and I, he came over and demonstrated one day, and I can't honestly remember whether it was P2 or a P1V setup, but he did manage to get audio working over HDMI. Because, I remember we tried it with some different monitors, and some worked and some didn't, I think, from memory. But it's worth asking the question. Roger, it's a bit early for him to do these kind of conferences, but
okay. Well, I'll reach out to him on the forum.
Yeah, exactly. Just ask.
Yeah. Well, thank you for clearing that up. Yeah, that makes a lot of sense.
Oh yeah, you bet. Yeah, someday I want to get into all that kind of stuff too.
Actually, I did another question regarding the alt instructions. and that is that when you do something like Alt-I, and it loads up the R, D, or R or D and or S, that puts it into pipeline. And so the value that had been in the register that was pulled in to the pipeline, that register can then actually be changed, right? There's no,
Right.
I don't have to like wait clocks.
No. It
after
happens
that. Okay.
quick. And you know,
Okay.
there's a whole bunch of unexplored stuff. You can compound alt instructions. You could have alt instructions modifying alt instructions that modify some instruction that is the point of what you're doing.
Yeah. It was mind bending enough, I think, to work with like alt that's already changing all three parameters.
Oh yeah.
I think having
if you
an
just
alt.
say, yeah, just a straight Alt-I will use a constant for S that will swap out the entire instruction.
Yeah. Okay. Yeah. You know, I might actually be doing that because I'm using the alt stuff in two different places, in a different way in the two different places. Okay. Well, thanks. That answers all of my questions. Thanks a lot.
Yeah, you bet.
Yeah, you got a lifetime to figure it out, Bart.
Sure. But, you know, it's impatient though, you know, like I want to see the thing come to life.
Hi, Chip. I have another question for you. With your current debug output, the nice thing is that you can compile with debug or without, and then the debug output is not in there. Is it possible to send data with that debug statement that a normal terminal can output it?
Wait, is it possible to send data with the debug statement that what can output it?
Just normal serial data, because then you could kind of put some debug statement in and send it to processing.
Oh yeah. That's what. Yeah, the raw debug statement can send anything.
Yeah.
But see, I use that little backtick thing as like a little trigger character for the debug displays, the graphical debug displays to key off of. But yeah, it's just serial. The debug statement just spews out serial. It can be whatever you want.
So when I send just a simple string in debug without any backticks, it would basically send that string.
Yeah, you can totally control what gets sent out. Yes.
So then kind of attaching to processing shouldn't be a problem.
Yeah, it may not be.
People who wants to do it, I mean, basically, you know. But the nice thing on the debug is that you can compile with and without, which is kind of like an if-def, which you don't support yet.
Right. Yeah, I have to do Control F10 to run this scope display. If I just do F10, it compiles the program without any of the debug statements, and then it runs it, and it doesn't open up any debug windows.
Yeah, that's very nice. Slowly, I like it.
Yes, if I just run it, that's it. It's running now, but it's not doing anything. But Control F10 causes the extra compilation and the debug window to open. Hey, Ken.
Yes.
What's next? What should we do next? Here's my situation here. I've got all of my wife's brothers are here except one. We got 4 brothers and 2 of their kids.
Yeah, you've done your job today, so we can let you go.
All right.
And we'll end this if that's okay, because I have similar obligations, unless somebody else wants to take over host and keep the chatting going, which is an option.
Now, Michael could do that.
I have a quick question.
Yeah, go ahead.
Chip, I just tried to download and run Pnut 35B with the ADC on my retro board, and I'm having issues. It started off, I couldn't find it. I'm not sure whether it's a 2 megabaud issue, because I can see it's outputting. Runs perfectly fine on the eval. So I know the code and that's working. Can you slow the speed over the interface in case it's my UART not keeping up, my USB one?
You can put a delay command into the debug statement.
But I can't change it from 2 megabaud. It's fixed.
No, it's kind of all set up that way. Wait, can you do that? No.
I can download it to megabaud, and I download with load P2 fine at 2 meg, and I'm loading big files like 128 KB. No worries. But I've just got a little bit of a loss as to where to look.
It would be nice if the debug output could be configured to different baud rates.
Yeah, I know it would be. So I'm not sure.
I'm not sure that that's the issue, because I had trouble finding the board in the first place. In other words, it wasn't finding the P2.
Hey, hold on, I gotta step out. I'm gonna be right back. My brothers-in-law are leaving right now, but I gotta talk to him really quick. I'm gonna be right back, okay?
Okay, yeah, you take your time, Chip.
Hold on.
Sorry, I didn't realize he was in that much of a hurry.
Well, it is December 22nd. It's family holiday times.
Yeah.
He does this routinely, so we'll have to let him go at some point here.
Yeah, no worries.
We'll come back.
I can ask him over email. So that's not an issue.
So Ken, I just was scanning some of the processing stuff, and it looks like you could just send it the serial stream coming out of the debug stuff and write a script to parse that serial stream and produce visual displays. Like,
would you even need to do the parsing? Can't you just do that straight out of the P2 code?
Well, no. I'm saying the P2 output, the serial output that it outputs for the debug mode, is a string per output, right? That we would need to parse to then draw the appropriate line or data from that debug serial stream. But what I'm getting at is we don't have to like convert the serial stream to some other serial stream. We can literally just process it right in processing with scripting to, parse.
Quite doable then.
It seems like it's very doable. It's just the main thing would be hooking into that serial stream appropriately so you can see the displays. Like, because right now Peanut, when you hit Control F10, it produces the window and is holding on to that serial port.
Yeah.
So we would need a mode to be able to run on the P2, but not consume the serial port and let processing consume the serial port.
Right.
What I did was I sent the data to a COM port on the computer, and then I used the processing to directly pick up whatever data was coming through that COM port.
Yeah, that's what I was saying.
I had like 6 different sensors that I wanted it to pick up and display at once, so I had to format that data
Roy,
to go to each graphical.
There's a debug pin variable which you can direct. Does that help you?
So you can set which serial pin the debug output goes to?
Correct.
Okay, yeah, that would work also, but I think it would work fine with the main one. We just need the ability to run a program with the debug output without Peanut bringing up the Windows itself and
I think when you
consuming the serial port.
Correct. I think what happens is when you set the debug pin, it no longer consumes the port.
Right, but I'd want it to use the regular serial port, just like the Peanut does. Like, the whole idea is that you would run MicroPython on the P2 and run a program that has debug stuff in it, and see it the same way you would if you ran like with Mu or whatever. And similarly, when PropTool or Peanut, when it runs, I want to be able to compile and run, but not go to those displays, go to processing instead. It's just a technical thing of taking over the serial port, right? Peanut currently holds on to it.
Yeah, and a lot of the like Arduino tool chains, they kind of manage the serial port so they can play these funny games. We'd have to have a level of coordination somewhere in the system, and I don't know how to abstract that out, but I think everybody kind of sees what the path forward might be on that.
Yeah, and it seems like the value of it really is more with Mu and Python than it would be with Windows and PropTool and Spin2, because Chip's given us this fully integrated, and it's coming into PropTool. So
yeah, but we can't add our own. With processing, we can add our own and do whatever the hell we want.
Yeah.
Right.
And another part is that processing runs on different OSes.
Big point.
It runs on Linux, it runs on Mac, it runs for every Arduino guy. I mean, I never had one of them, but basically it is, and we talked about that before, that it would be nice to have also those debug windows from Chip not integrated into PropTool, but as a single application, so you could use it from, I mean, even talk to them screens from MicroPythons.
Yeah, well, that's what Gerald is working on, the C++ port of it, which would be sort of a standalone app to display all the windows from the serial stream.
Yeah.
And if we have that, then that can be used with like FlexProp and anything instead of being locked into PropTool.
Then we would basically need one of those constants for debug, like debug pin, and a constant for debug program, which should, or maybe use.
I don't think we need any of that. It would just
like
use
that.
the same serial stream that it already
Yeah,
does.
just straight serial stream.
To prevent them screens to pop up, we would need kind of a control F10 with debug, but without opening the debug screens, so we can use processing. Like, I mean,
yeah, it's just a option on PropTool to run with debug, but don't bring up the debug windows. It would be very easy for Jeff to add that, and then we can, and then processing can be running, and we can just attach to the COM port after the P2's running and see all the displays.
So here's a wacky idea that someone kind of alluded to in the chat, and that's, you know, what if the PropTool, you could just tell it, hey, whatever comes from the serial port, emit it to a UDP port, maybe even a multicast port somewhere, that dumb networking code can pick up on that, whether it's processing or just about anything else that can open simple sockets. I don't know. Maybe I'm just written too much network code to be useful in this context.
Oh.
What would be nice with a readout like this is if you could put what you could do if you were using processing, is if you could put a graph there so somebody looking at it could tell what range and what amplitude and everything these different sine waves are at.
Yeah, all the scales of the
Right.
axes. And then you could also probably even do things like capture single instances of a display and save them, and keep a running set of data, so that the data, like this sine wave that we're seeing now, could go in time depth-wise, and so you would see a surface of the sine wave changing shape, right?